So thanks to the organizing committee for inviting me here. I guess my talk is quite different from the previous one. It's mainly Bayesian and high-dimensional in some settings, but not much on the computation. We just need to use some computational machinery which has already been developed. So this is mainly the work of my PhD, Li Feng Ye at UCL. And then it's in collaboration with Alessandra Guglielmi at the Polytechnic of Milan and Stefano Favaro in Turin. So basically, when we started to think about this problem, this is what we had. We had a group of patients which we observe at different time period. And we want to look how these patients cluster according to some characteristics. So you see them at time 1, and I guess this is the bottom. And they cluster like this, and then you look at the clustering of the same patient at time 2, and you look at, is it the same clustering of the patient, or some people switch because for some reason, and the same you do you look at the clustering structure of your patient at time 3. And basically, the idea is like, okay, this patient usually showed the problem we had in mind, but this is more general setup. It was, okay, the patient usually have different reply to therapy, and so they evolve through time in different ways. And obviously, the clustering structure might change. Sometimes doesn't change much over time, but sometimes can change drastically or can change a bit. And we were thinking about a model who could accommodate all these different scenarios. So that was the problem we had. So that's what I would like to do. My talk is basically on Bayesian nonparametric. So what we were interested is to develop a type of models, a type of prior distribution for a collection of distribution of random distribution that evolve through time. And we still would like to do clustering, have possibly introduce covariates in the model. We would like to do prediction, but basically what we would like to do predict is a random distribution at time t plus k, say. And still we would like to be able to do some sort of inference, so to run some sort of posterior inference algorithm, and basically be able to share information across time period. So this is the idea of this talk. So as I said, if I fix my attention at time t, then I have an observation at time t, y1 to yt, and I take this observation and I would like some flexible distribution. I don't want a parametric distribution, I want something a bit more flexible. So a typical solution is Bayesian nonparametric is to convolve a parametric kernel k here with some distribution gt. And gt is the mixing distribution at time t. Then if you put whatever is your favorite prior on G, for example, a Dirichlet process, a polyatry, a Pitman prior, then you end up with what is called a Bayesian nonparametric mixture model. And if you look at the literature, everybody's got his own favorite prior, and they are particularly passionate about it. So the one I know better is the Dirichlet process, and that's what I'm going to use because actually in the setup is arguably the most famous nonparametric Bayesian prior. So what I need you to know, this is my usual introduction slide, 3 minutes introduction on the Dirichlet process for audience who might not all be familiar with it. Basically, the Dirichlet process is simply a probability model on distribution, and it's got 2 parameters, a precision parameter alpha, and then a base measure G0, where it's basically the centering distribution of the process. And the main characteristic that I'm going to exploit in this talk is that G is almost surely discrete. So what's going to be important here for what comes is that since G is almost surely discrete, Sethuraman showed that it admits a representation as a countable mixture of point masses. So this, the location of point masses theta h are basically IID draws from the base measure G0, and the weight of this mixture is what they admit what is called the stick-breaking representation. So the weights are built upon this beta random variable, IID beta random variable, and each weight basically is like you think about the interval 0, 1, and you keep on covering with small pieces. So the first weight will be equal to the to the first beta random variable, and then the other weight omits this definition. So this actually is this construction is basically the trick that most of people use when they build a dependent prior on a space of distribution. And so, as I said before, what happens in application is to convolve a parametric kernel with some distribution G to which we assign a Dirichlet process prior. And this is very, very typical in application. And since obviously G is discrete, so basically what you're doing is actually when you take a Bayesian nonparametric mixture, your sampling model becomes, say that your kernel is a normal distribution, then your sampling model becomes simply a countable mixture of a lot of normal kernel, where the location here comes from the Dirichlet process, so from G0, say for example, and the weights also come from the Dirichlet process. And since this is a mixture at the end of the day, it emits the usual latent variable representation for mixture. So you have the distribution of y given theta I depends on theta I, and theta I comes from G, and G has a Dirichlet process prior. So this is why the Dirichlet process is used for clustering. Obviously, this is a discrete distribution. There is a probability, a positive probability, that two observations will share the same I. So when two observations share the same theta I, then we say that they belong to the same cluster. So the Dirichlet process induces a random partition of the observation. So what I said up to now refers only to one time point. Obviously, our model, so I could take one time point and cluster my patient using a non-parametric mixture. But what I want to do is actually to do it in a dependent way. Right? So my problem is a bit different because my observations are also associated to temporal coordinates. So each observation at time t has its own gt. So I have a collection of gt, and what I want to do is actually to induce dependence across gt. And this is very reasonable in application, because you might think that the property of the distribution at different times, so of ft here, should be for some reason they could be similar, they could share the same mean, they could have the same tail behavior. Anyway, whatever is your favorite distance between distribution, you might think it's small. So this is the problem we want to do. We want to create a dependent prior for this collection of random distribution indexed by time. So that's the problem. And an easy way of doing it is actually exploiting the stick breaking representation, because since each of these GT is a Dirichlet process, you can represent it as a countable mixture of point masses, but now both the location and the weights are indexed as well by t. And so you can think that the theta t are a realization of some stochastic process in t, or also the weights of the mixture can depend on t. And this type of problem of specifying prior for a collection of random distribution has been studied more extensively in a regression context. And the solution that have been proposed, they all exploit, there have been various solutions in the literature. I think there are three main categories. The first one, if you want to introduce, say, temporal dependence, I can take my G0 and I can specify some sort of, say, autoregressive process for G0. So I can create some G0t, and you would draw your the location at time t from this G0t that depends on time. So you're introducing actually dependence in the base measure in G0t. This is a very simple thing, extremely efficient computationally, because you can still use the marginal algorithm for the Dirichlet process. It's not very difficult, but it's a bit limitative in application. So the other solution would be to take all the location of your different GT and make them time dependent. Once again, this is okay, but it's not very efficient. So the other idea is to introduce dependence through the weights. So make the weights dependent through time. This is much more flexible approach, and the problem with it is that sometimes it becomes a computational nightmare. So when you think about this type of solution, you actually need to think a bit more carefully about computations. And there is a completely different approach is that is also being proposed in the literature. It's actually taking each of these GT and make themselves a mixture of a common part, G tilde, and then a time-specific part. But this is completely different in spirit from what I'm doing here. So this is the idea. The strategy we take is because is the one of introducing dependence across distribution by making the weights of my mixture dependent. So I'm going to take all distribution here, so this distribution here, and I'm just making these weights here vary through time. I keep the location fixed, so all the random probability measure will share the same atoms. And it can be shown that under certain conditions, we can approximate basically any density. That's why it's a bit more flexible trying to put the dependence in the weights. It's basically, we can approximate any density with any atoms. And obviously, by varying the weights, you can make this distribution arbitrarily close or arbitrarily far apart. So this is the idea. And this problem of temporal dependence of random distribution has been studied as well. This is some people, here some reference to people who have tried to solve it using the Dirichlet process. But as I told you before, the Dirichlet process is not the only parametric prior, so there are also some proposals in the literature using the Poisson-Dirichlet process, or what is becoming now more and more popular, normalized completely random measure. There is another approach that tries to do exactly what I'm doing, but instead of specifying a prior on the collection of random distribution, what they try to do is to specify the prior on the partition at different time, on the random partition at different time, and then try to connect the prior on the random partition at different times in some ways. So this, I think, is something that is quite new in the literature. There are not many papers, and it falls in the category of covariant-dependent random partition model. But from what I have seen, it's quite a computational nightmare. It's been my impression that it's not. It's still like something they are starting to develop. And the other, but basically, in reality, what I'm trying to do here instead is actually try to specify the prior directly on the distribution of the data, on the collection of the distribution of the data at each time point. And the trick I'm going to use is to use some transformation of the beta random variable that are the essential ingredient to build the weights of the Dirichlet process. So, having said that, there are some approaches in the literature that try to do the same thing. So they had the idea, let's see if I can create some sort of temporal dependence in the beta random variable, so I'm automatically creating some weights, some temporal dependence in the weights of the Dirichlet process. So the first one is by Taddy, and it's just a paper in 2010, and it defines this beta autoregressive stick breaking process. So just I put up here the stick breaking construction. So what all these things and me too we're trying to do is to find some clever transformation of this beta random variable and make them time dependent. So the way of Taddy's way of constructing the beta random variable is to use this combination. Each beta random variable depends on the previous one, but the coefficient are given by other two beta random variables which are independent. And then obviously the level of dependence is controlled by this parameter rho between 0 and 1. So beside whatever it is, this type of construction implies that the correlation between two beta random variables, no matter what is the lag between them, is always positive. Then we have done some simulation, and for some reason that we haven't quite figured out why, the clustering structure at time 1, where you have just a standard Dirichlet process at time 1, and the number of singleton, like cluster with only one observation in time 1, is completely different from the other times. And the other problem with this construction, but Tad is quite upfront with it, is that you can obtain very different clustering structure at different time period, but the predictive distribution are quite relatively similar. So the clustering in this type of model is quite unstable, and to be fair, is very upfront to it. What we don't really manage to understand is why this is happening, but we've done tons of simulation. So another process that is also in the literature, more recent, 2018, is to take always this beta random variable, and as a transformation of this beta random variable is to define this beta random variable as a function of two normal random variables. This zeta square, which is simply a normal 0, 1, and is common to everybody. I've been here a bit sloppy notation. It should be psi t k, but just not to be redundant with notation. And then these are the normal random variable eta t, which actually defines an autoregressive process of order 1. So eta t given eta t minus 1 and this phi parameter is the usual autoregressive one model, right? So it depends on eta t minus 1, and this is the autoregressive coefficient, standard autoregressive. So this is be more similar to what we are doing. What are the problems of this setup? If alpha is greater or equal to 1, you are always going to have a correlation between two beta random variables greater or equal to 0.5, which is not always desirable. So the same weights, for example, the first weight at time 1 and the first weight at time t, always have a correlation above 0.5. The eta appears here squared, so the correlation between different times will always be positive. And in reality, if you do a bit of an extra work, you make also the location dependent, you can sort of overcome all this limitation. But the price is to complicate the model a bit. But you can do that. So what we are going to do? So in reality, once again, we want to do the same thing. We want to introduce this dependence through weight. So we have a set of time-evolving random distribution. So we were looking a bit around for way of doing it. So we thought, let's have a look at the Coppola literature. And the Coppola literature, we ended up reading this nice paper on marginal beta regression by Guol and Barin, which is based on this theorem that all of you knows better than me, which is the probability integral transformation, I guess, which says simply that if you have a standard normal random variable, and f is the CDF of a beta distribution, then with parameter a and b, then y, which is defined as the inverse CDF of the beta, evaluated in the standard CDF of a normal in epsilon, this random variable y is a marginal distributed as a beta a and b. Okay. To be fair, this type of transformation was also mentioned in the first DDP paper, the original DDP paper by McEachern. We just never realized until we saw it in this paper on marginal beta regression. And so now I think you can all imagine what's going to happen. How do I define the time evolution from the weights? So I consider an AR1 process, A epsilon 1. It comes from a normal 0, 1, and then epsilon t is as a mean that depends on epsilon t minus 1 plus this normal error with variance with mean 0 and variance 1 minus psi square, standard AR1. So that's it. Then I take how do I create my stick breaking construction at different times? I take an infinite number of these AR1 processes, right? Then the beta random variable psi tk, so at time t for beta random variable k, are defined through the inverse CDF that I showed you before, the transformation I showed you before, and then the weights at time t have the standard stick breaking representation. The location of my random measures all draws from G0, and I'm keeping the location fixed through time. And this is basically my GT. I just need to get the right psi tk and the right WTK. So it's very easy. I define an R1 process that for each of the, you have to remember, when I build my Dirichlet process, I need an infinite number of basically of beta random variable. And here I'm taking an infinite number, if you like, of AR1 processes. And this infinite number of AR1 processes will allow me to define the infinite number of beta random variable that I need to build the weights of the DP. So analytically, this transformation, unfortunately, is not as nice as others to work and try to understand. What we have tried to do, it does have some nice properties. First of all, it's very easy to generate every GT because you just need to generate a lot of AR1 process, and everybody knows how to do that. The marginal distribution of each epsilon t is still a normal 0, 1. So the distribution of the psi t marginally is the beta with the desired parameter. If you fix them equal to 1 and alpha, then you go back to the Dirichlet process. So each GT has marginally a Dirichlet process distribution, which is also nice. The psi t, the sequence of psi t inherits the same Markov structure of the epsilon t, and therefore, in some sense, also the GDT is an IR1 process. And it's obviously, in this setup, very easy to derive the k-step predictive distribution. Remember, here we're not trying to predict a point. We are trying to predict a distribution. This is the random object, is the distribution. And the nice bit of this construction that this thing here becomes quite straightforward. So we actually have tried to understand better the evolution of the weights through time. And as you can imagine, because of the transformation, it's not super simple, but we have managed to derive the conditional law of psi t given psi t minus 1, and it can be shown is the same law of this random variable here, and the conditional law of psi t given epsilon t minus 1, which is basically this, which might not look very user-friendly, but it's very easy to simulate from it. But just I put here some pictures, just to give you an idea of how flexible is this type of modeling. This is the conditional law of the first random variable, of the first beta random variable at time 2, given the first beta random variable at time 1, which is equivalent to the conditional distribution of the first weight at time 2 given the first weight at time 1. And here for the first weight when is equal to 0.9, so when I have a big cluster at time 1, and the first weight at time 1 equal to 0.5. So the size of the cluster is a bit smaller. And here for different value of the autoregressive parameter psi. And I fix alpha of the Dirichlet equal 1. So when psi is equal to 0, which is the black line, you can see that the beta random variable are simply uniform, and here it doesn't matter what happens to psi, you get your usually uniform distribution. If psi equal to 0.9, so a very strong dependence, obviously you're going to have the conditional distribution centered very close to 0.9, while here is going to be centered even more around 0.5. So you will have the first weight at time 1 very similar, at time 2, sorry, very similar to the first weight at time 1. And then when psi is negative, here obviously since it's so strong, it's going to be centered more on the first weight at time 2 will be quite small. And here you just basically are adding noise. So the idea here is like this type of construction can accommodate a variety of shapes over the unit interval, so it should be quite flexible. So how do we do posterior inference? So this is where the problems start. So first of all, we do posterior inference based on the truncation of the DP to L components. And we need to extend basically the usual block Gibbs sampler for DP, which was proposed by Ishwaran and James in 2001, to include a particle MCMC update, because to simulate from the distribution of the weights of the DP. So since basically this is a mixture model and we are truncated, so you can think about it as finite mixture model, you will have at each time point an allocation vector, so which will tell you to which cluster the observation belong. And then you will have the vector of the weights of every cluster. So what you need to do, and this is for at each time point, you need to sample from the joint distribution of the weights at every time point, so W1 to WT, given the allocation at every time point, and then the autoregressive parameter psi. No, you cannot do anything like standard things like the forward filtering, backward sampling, because all the one-step predictive distribution, WT given WT minus 1, are not available in closed form, so you cannot do them. But you can actually employ PMCMC. And you can use also the prior to generate the sample epsilon t. And in all whatever we are doing here, we are exploring the fact that the law of the weights, of the conditional weights, WT given WT minus 1, obviously it depends, is equivalent to the law of epsilon t given epsilon t minus 1. And if you do this, basically at the end you get an SMC approximation of the desired conditional distribution, which is the distribution of all the weights at every time, given the allocation vector at every time point. So you get the usual SMC approximation, and then obviously you can simulate from it. So just a slide of simulation. Not sure how much time. Okay. Okay, perfect. So to show that, the model is doing what we expect it to do, these are just 3 different simulation scenarios. Each of them has simply 4 time points. In the first one, here what I'm showing is inference on psi, on the autoregressive parameter. And we wanted to see if we were able to accommodate different scenarios. So here we just generate data independently from a normal distribution at every time point. And basically there is 100 observation at every time point, and there is no time dependent structure. And in fact, the autoregressive parameter is centered around 0. Now what we do, we generate data at type 1 from 2 clusters, and then at time 2, 3, and 4 individual remain in the same cluster, and the distribution is the same. So here you have a lot of dependence, strong positive dependence, and this is the posterior distribution of psi, and once again is strongly centered close to 1. So also this seems to work. Then we did something a bit different. We generate data from 2 clusters at time 1, and then for the subsequent time points, individuals have a 50% probability to stay in one cluster or to switch to another one. And we also change the distribution at different time points. And if you look at inference on psi, now it's centered around the negative value. So at least that gave us an idea that more or less the model was doing what we expected. And so now I'll show you just 2 simple examples. The first one comes with, this is a very typical problem in epidemiology, which is space-time clustering for disease mapping. So what you are interested is to model the disease incidence of whatever is your favorite disease. And usually disease incident data or mortality data come either as counts for a specified region and a specified time period, or as rates. So the data we take are breast cancer incident data for 100 metropolitan statistical area, which are public available. And we consider data from 2004 and 2014. Now, when you do disease mapping, you also need an idea what is the population size of each area. And we get the population data from the US Census Bureau. Unfortunately, they are available only for year 2000 and 2010, so we just estimate the other one by linear regression. And so what the main goal of the analysis here is to identify cluster in space of time. So basically to identify spatio-temporal patterns and possibly predict disease risk and predict disease risk at the end of the day. So the model is quite simple. Is quite the likelihood. I mean, the usual likelihood in typical likelihood in epidemiology. So the data are breast cancer incidence counts, which is basically the number of cases in region I at time t. NIT is the number of individual at risk, and RIT is the disease rate in area I at time t. So the model, the likelihood is simply Poisson likelihood with parameter NIT, which it's given, and RIT, which is the disease rate. Now, the model for the disease rate on a log scale is basically simply the sum of a random effect that depends on time, MUIT, plus a spatial component phi I. So MUIT, given GT, we assume that comes from GT, and on this collection of random distribution, we impose the RDP prior, which I've described up to now, and then this is just the parameter of the Dirichlet process, is just a standard normal distribution. Now, phi here instead captures the spatial component, and this is once again is one of the standard spatial prior that are widely used in the literature. So the vector of the phi is normally distributed with mean 0, and this is the precision matrix, this thing over here. Now, tau square basically controls the amount of variation between the spatial random effect. Rho controls the strength of the spatial correlation, and C is a matrix that actually specifies who are your neighbors. And this is all very standard in spatial statistics. So you will have a 1 if two regions are neighbors, -1, sorry, if your region are neighbors. On the main diagonal, you will have the number of neighbors for each region, and then 0 otherwise. And then you complete the model by specifying some hyperprior distribution. And this is the posterior inference on clustering. So these are all the different regions at year 2004, 2007, 2011, 2014. And you can see here the color corresponds to different clusters. And we start, I think, and the clustering estimates are basically being obtained by minimizing the binder loss function, because there is another problem, is like how you summarize clustering output. There is a huge discussion in the literature. And I mean, whatever is your favorite one, but we take the clustering that minimize the binder loss function. And you can see that some of these regions move cluster. Here we go from 4 to 3, and then back to 4, and finally in 2014 we just identify basically 2 main clusters. And obviously you can look at also over time a co-clustering probability across time between the 2 regions. So you can look at the and you can see how much they change in these 10 years. So they try to, basically the region become more and more uniform. And what about posterior inference on the correlation parameter? So this is about temporal correlation. This is psi, and there is a strong temporal correlation. So this is the parameter of my RDP process. And this is also the spatial correlation parameter rho, and there is also a lot of spatial correlation. And just to finish, just to give you an idea of what the model could do, this is a bit of a forced model. This is not the right model for this data, but just to give you an idea that we can basically accommodate different scenarios. Here we have data. This is a typical clinical trial. which aims to find out what is the biggest dose of chemotherapy you can give to a patient without killing him, basically. These are all terminal patients that suffer from some type of cancer, and basically here to try to find the biggest dose of chemotherapy. CTX is the anti-cancer agent. And since they receive such a strong chemotherapy, the other drug they receive is this other drug, GM-CSF, which needs to mitigate some of the side effects of chemotherapy. Because obviously, when you get chemotherapy, basically it kills a lot. Your white blood cell count falls down drastically, and you are at risk of infection. So it can be very dangerous. That's why they give the second drug. So in reality, these are in nature longitudinal data. And you can see each of the gray line corresponds to a different patient. They all start more or less, this is the log WBC counts. These are the data. So we want to model the trajectory. If I was really doing this analysis for other goals, I would model the overall trajectory over time of this patient. They all start here, the common baseline. Then at the start of the chemotherapy, you have a huge drop in white blood cell counts. And then an S-shaped recovery starts about at this time. So I've just fixed my attention to 3 time points, one more or less at the beginning, one when basically chemotherapy should have reached its drastic effect, and then one in recovery. And so the model, once again, I'm modeling the log blood cell counts, just normally distributed, with some mean and some precision lambda tau it. The mean is the combination of a regression part that includes the drug level, so the therapy, and the random effect that varies over time. Now, both M and tau here depends on time, and they come from a distribution GT, and the collection of this distribution comes from an RDP. So this is the standard model. And what happens here, you can see that if I try to make inference on psi, now the distribution is centered around the negative value. And he didn't like my talk, so he's shutting me down. And basically, and actually, if you look at it, it's quite nice. These are the 52 patients colored by, this is just the plot of the random effect for the 52 patients. And you can see at the beginning, you could see it in the plot, they are all quite similar. There is only one, this patient that is the odd one out. But then when the chemotherapy starts, things change. Most of the patients fall deeply, but 2 patients seem to resist quite well. And then what is a bit more different, where there is a bit more variation, is actually in the recovery. And this is quite nicely captured by the predictive distribution. You can see that at day 4, more or less, is around 2, and there is not much variation, just one patient here. Day 14, day 9, which is the dip in white blood cell counts, you can see they all more or less drop of the same amount, where there is a huge difference, more difference among patients is actually in the recovery. So it's how these people recover from chemotherapy. And this is about it. So this is what I wanted to do, is just to present this model, which is based on a Dirichlet process, and it's a model for time-evolving random distribution. In reality, I think it's quite easy to work with and allows for this time-dependent clustering, and it's actually quite easy also to predict future time, random distribution at future time period. We thought that the PMCFC was working quite well, and we were thinking to extend it to more complicated, if possible at all, temporal process for the latent variable, which are at the basis of everything. And this is it. And thanks a lot for listening.
Interesting to see that you connect the GT to your distributions. In terms of those Gs, what is the visibility of the dependence like when you plot successive realizations of the GTs, how much can you suspect that there is this dependence? Because when you create a dependence at a very
basic level.
Low,
so you can look at
intensity level, and then what you're interested in is the correlation between the GTs.
So one thing yes, so we have tried, because for other things you can do the calculation. So we have tried to look at the distance between the weights. We have tried to do that, because you can simulate it and see it. So I guess you can summarize the distance between the GT, a posteriori or a priori, I mean a posteriori, by looking at the distance between the weights.
Just to understand the model, because this is a model that is created ex nihilo. And so
yeah, but basically, okay, so if you think about, okay, look at this picture, right? So this picture, in theory, they all have the same representation. The location of the mixture are always the same, right? So what is changing here is only the weight. So in this distribution here, weight at 2, the weight at 2 was very big, right? Because you got a nice mode. Here, you can see that the weight at 2 was is much smaller. Basically, you can look where the different mode of the different distribution at different times are putting more, where you have more weights, where you have the different modes. In theory, those locations are everywhere, right? Does this answer your question? No, I can see it in your face. Maybe I didn't understand your question.
It's more basic, it's more naive as a question. It's that you are creating an object that is a sequence of dependent random functions.
Yes.
And is there a way to translate this dependence in somewhat intuitive aspects?
Okay, no, I don't think intuitive. I mean, you can.
That's why you did a prior level.
Yeah, no, we tried that. Okay, so we wanted to try. So for other model, we were able to say, okay, the distance would be this, and I can plot the distance between the random distribution. Here, no, we can't really do that. No, we try. If I understood your question, to summarize it in some measure, you mean? Yeah, we can do it by simulation if you like. Yes, we can do it by simulation. But look, what we wanted to see was the weight behavior, like, for example, of the biggest component. How does it evolve through time for different value of psi? We wanted to do that. If we didn't manage, we only managed to do the xi, the little beta random variable. But then the xi get in a very funny, I mean, the stick-breaking construction. So analytically, I can do, so by simulation I've done a lot and I've seen a lot, but analytically I do not have a very nice measure to show you. I only have it on the xi, the conditional distribution, that's it, which is the plot I showed. But no, the most interesting thing for me was the weight, how they evolve through time. But that, we've tried and tried. So by simulation, yes, I can see how they evolve a priori through time, I can do all that kind of things. But if you're asking me a nice little measure, I do not. No, I don't have it.
Any other question or comment? One question. Is there any specific reason for the choice of AR, the process for epsilon?
This one is because of all, it's easy to work with.
The stationarity is important or not?
Yes, yeah, I think so. I think for both me and to get the right mark, yes.
Okay, yes, okay. Next time the speaker again.